Alright, welcome back to the next concept on normal distributions. From this point onwards, this concept, your understanding in what normal distribution is critically important. Okay, so it's gonna basically set the whole foundation for this chapter, this video onwards. So I'm gonna recap what we did in the previous video, and then I'm going to explain how it links to what normal distribution is all about. Okay, so in the previous video, we talked about what is a continuous random variable, right? And as the name suggests, there are two attributes to this variable. The first thing is that it does not take on any discrete values. It takes on a value from a set range of values. So from 0 to 10, I just pick one value, right? It can be 9.9999999, or it can be 8.765432 right? So the value that we pick is not specifically a value. You can just think of it as just, you just pinpoint at one value within the whole range of values from there onwards, right? And the second thing is that this value that we pick is by chance. So in other words, it's picked by chance. And with the element of chance, there is this thing called a probability, right? Which is something that you did in the previous question. So in regards to your syllabus, this probability that we talked about just now, right? For instance, when we have a graph like that, and then over here, this is my probability density, and then this is the values of all the x values, right? The range of the x values. So in your syllabus, the most typical kind of distribution for a continuous random variable will be what we call a normal distribution. Okay, so continuous random variables, right? They can have many different kinds of distributions, right? The probability can be distributed in many different ways. A lot of it is not within the scope of your syllabus, but the only distribution type that is within the scope of a syllabus is only your normal distribution. Okay, so normal distribution is the only one you need to care about. So what are the features of a normally distributed curve, right? A normal distribution curve. So a normal distribution curve, as what many of you might already have heard before, is what we call a bell curve in short. So some features of a normal distribution are as such. It's a bell curve whereby, oops, let me just try to draw this properly again. Down here, right? And then this is called fx over here. So once again, the equation, you don't need to know what the equation is, right? And just for your information, the equation is fx equals to 1 over your sigma, not sigma, but your standard deviation, e x minus mean square over 2, this one square, right? So the equation is very complex, and you are not required to know this. So scrap it out, right? It's just for your information. Just for your information. But what you need to know is how to read it. So what makes the bell curve so iconic is because this is the center value, right? It is symmetrical about the middle value, right? And this is basically for most things that are continuous random variables. For instance, your height of the people in your class. For instance, let's say the scores of an exam, right? If let's say the marks can go down to like very small percentages. Nature happens in very miraculous ways such that most things are normally distributed. For instance, let's say you have your whole entire nation A-level score, or your whole nation O-level score. You have over 30,000 people taking the O-levels every single year. And when you have such a huge group of data, and with each score, right, I don't know how they grade it, but with so much scores, when you actually plot out the probability distribution curve, you realize that it actually kind of resembles this shape over here, right? And that's just how things naturally occur in real life. So that is what normal distribution is just a shape of a curve that we will be discussing in detail for this whole chapter, essentially. So want to preface some things. Under the normal distribution, right? If let's say a continuous random variable is said to be normally distributed. Okay, so I'm just going to write it here. If a continuous random variable, right, is said to be normally distributed. So if we say that, that means we know that the shape of the distribution is a bell curve. Okay, and if the shape is a bell curve, we can immediately tell that the expected value is the mean value, and the variance of this is your standard deviation square, right? So these two are your very typical symbols, and later I'll show you how to actually calculate all of these using a GC. So once again, you don't need to know how to calculate this for a continuous random variable. All you need to know what to do is to use your GC, which I'll show you in a bit. Okay, so for this curve over here, right, let me just annotate this curve over here so that we know what exactly is happening. This over here is the mean value. Okay, so the center value will always be the mean value over here, the mean value. Now, if I were to draw a line from here to here and from here to here, this distance and this distance is your standard deviation, okay? And the first standard deviation, okay, let me use a different color. From here to here, you have about 68.3% of all the data will actually fall within this range over here. So it's all with respect to the center line, okay, the mean value. And then if I go another round again, let's say I go one more time, right, and then I extend one more standard deviation to the left, and then I extend one more standard deviation to the right. Now, over here, you will have about 95.4% of all data points will actually fall within this range. Okay, that means anything else over here is the remaining, right? You take 100% minus 95.4%, you get 4.6%, right? So 4.6% actually lie outside of this. You need to know how this visually looks like, and it will help you a lot later in your calculations. But just note that everything is all measured against the mean value, which is the center value. And our standard deviation tells us how far, so-called how far, the data that we are trying to assess is from the middle line, which is the mean value. Okay, so you don't need to know these percentages in detail, but I'm just, illustrating to you what is actually going on underneath the hood, right, when we are learning this. And another attribute to understand is that this curve, right, it extends indefinitely. So just know that it doesn't stop. It actually extends towards infinity in other direction. Okay, and one more thing to remember is that the total area under this curve, so if I were to highlight this whole space over here, right, the total area under the curve is your integration from negative infinity towards infinity, has a value of 1. Okay, and the area under the curve represents the probability of a value happening. So right now everything is very abstract, and you might be feeling very, very confused because there's no values being inserted yet, right? So we are going to actually discuss this concept using a couple of examples with values so that we can figure out exactly how to appreciate this in real life. All right, so I'm going to be using this question over here to explain to you whatever I just said just now. Okay, in case you don't understand what I just said, this question will help you. So first things first, let's break down what this is. Okay, so the question tells us, given that we have a continuous random variable called x, so this is a continuous random variable, this dash and followed by this n over here, this portion means that that follows a normal distribution, right? This is what it means, that we have a continuous random variable that follows a normal distribution. Now, what about these two numbers? What do these two numbers actually represent? They represent the mean value, right? So this is the mean value, and this over here is the variance. So, you have your standard deviation, you square it, you get variance. So what this means is, let's say I draw the curve. Okay, I'm just going to try to illustrate this whole point over here with a curve. So this again is my fx, this is my x, and my probability distribution will look something like this, right? The middle value will be my mean value. So this is 23. This is my mean value. Now, if I were to go to the left by 1 standard deviation, this means that I'm effectively minusing away square root 12. Okay, so the first thing to note is that this 12 is the variance, the standard deviation squared. But if we want standard deviation, we need to square root this. So from here to here, this is plus square root 12. And then here will be 23 minus square root 12, 23 plus square root 12. And we know that this whole area underneath this whole curve, 68.3% of all values lie here, right? That was what I was talking about earlier on. So the first thing that this question asks is state the expectation value and the standard deviation of x. So the expected value is essentially just the mean value of a normally distributed variable, right? Because this value over here, the mean value, 23, just nice, is the value that has the highest probability density. So over a long period of time, the value with the highest probability density is the value that we expect the value of x to take on, which is just coincidentally the mean. So therefore, it's just 23. Whereas for the variance of x, right? Sorry, the standard deviation. The variance of x is 12. So therefore, from here, if we want to find out what is the standard deviation, right? Note that variance is your squared, and then standard deviation is without a square, right? So for this, you just need to square root 12. Okay, so these two are so far what we have. So now the question asks, evaluate the following probabilities. So how does this actually translate to what we see on the graph? For part I, they are asking us to find the probability between 20 and 25. So before we actually talk about this, I want to first draw on the graph how it looks like. So 20 will be somewhere here, right? I suppose. So let's say 20 is somewhere here, and then let's say 25, let's say 25 is somewhere here. So what the question is asking for is they are asking for what is the area of this graph, right? What is the area of this portion? Because the area of this portion would tell us the probability of a value landing between 20 and 25. Okay, so this one is something that you need to visually understand first before you move on in this chapter. All we are trying to do is to find out what is the probability of us picking a value, a continuous variable at random, and it falls between 20 to 25, right? And how it looks like on the graph is that we know that x is normally distributed with a mean value of 23, and the area under the graph between the lower limit and the upper limit of 20 and 25, this area is the probability that we're trying to find. Okay, so before we actually calculate this using the GC, because this whole chapter you're just going to be using GC, and most likely in the exams this is just one mark, right? Very, very free 1 mark. So you just need to punch your calculator correctly. But I just want to say that this over here is the same as this, is also the same as this, is also the same as this. Okay, so the symbols, whether it's inclusive or not, whether it is inclusive or not, we treat them as the same. Okay, we don't, we treat them as all the same. So treat all as the same. And the idea behind this is very simple. It's because in this context, right, let's say we say bigger than 20. Is 21 bigger than 20? Yes. Is 20.1 bigger than 20? Yes. Is 20.00001 bigger than 20? Also yes. Right? Is 20.00000000001 bigger than 20? Yes. Right? So in this context, it's very hard for us to pinpoint an exact lower limit, simply because technically speaking, the number can go on and on and on and on and on in terms of its decimal. So to make things simple, we will just take it as inclusive of 20. Because when we say inclusive of 20, then it becomes very clear that 20 is the lower limit, right? We cannot say 19.999999 because that's not 20. So we will always take it as, if it's bigger than 20, 20 is also included. Okay, so you just ignore that. So don't be confused by the symbols and don't think that, oh, because the symbol is different, then there's a different way of doing this. No, it's all the same. Okay, so that is the whole idea behind it. So now that I've illustrated this, right, I'm just going to write it here. So just take 20 as the lower limit. So how do we actually calculate this in the calculator? I'm just going to show you right now. Okay, first thing you want to do is you want to go to your GC. Okay, I'm just going to clear everything here. Then you want to click second, DISTR, and then you go down to normal CDF. So in the context of normal distribution, you have PDF and CDF. PDF is when you want to zoom in into one specific value. For example, x equals to 1, right? That's your specific value. But in the context of normal distribution, PDF is never used because of the reason that I said earlier, right? If I say 20, it can be 20.0000001. right? So usually for normal distribution, we will use a range of values. So 99.999% of the time, you will use number 2. Okay, so let me just clear all this. Right, I was just testing this out just now. So again, my lower value in this case would be what I want to find, right? And my lower value in this case is 20. So I'm just going to come back to my GC and click 20 here. Now my upper value would be a value of 25, because in this context over here in the question, I want to find out what the upper limit is, right? 25 over here, right? This green color line. So I'll come back to my GC, and over here I click 25. Now my mean value is 23, because that's what the mean value is. And whereas for this, just take note, you need to square root 12. Oops, square root 12. That is because the question gave you 12 as the variance, right? 12 is the variance, but we want standard deviation. So how do we find what is standard deviation from 12? We square root it. Okay, so we will square root this. Come down here, enter, paste, get this value. So what this value is the probability, 0.5249. So I'm just going to come back here, and I am just going to key the value of 0.5249 dot 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 dot. Oops, let me just zoom out, right? Which is 0.525 to 3SF, right? 0.525 to 3SF, which means that in the green color region over here that I have highlighted, this area under the curve is 52.5%, so to speak, right? But it's actually 0.525 lah, which is the same thing. Okay, so that's the whole idea behind it. So that's one way of doing this. Another way of calculating the same thing would be a method that I'm going to teach you right now also, using this opportunity. So this whole video, I'm teaching you many things lah. Another way to calculate this, instead of using 20 as the lower limit and 25 as the upper limit, you can also calculate this as x is lesser than or equals to 25. Oops, let me just write it below here. You can write it as x is lesser than or equals to 25 minus x is lesser than or equals to 20. You also can calculate it this way. So this is exactly why. Because if you say x is lesser than or equals to 25 over here, right? For this portion over here, I'm going to use a blue color line, right? For this portion here, you are effectively finding out what is this whole area over here, right? The whole area that I'm shading, right? As long as it's smaller than 25, you're finding this whole area. Then you minus away this whole area. So below 20 would be this whole area over here, right? So if you realize, if I take this whole big chunk over here, then I minus away this whole small chunk over here, what's left is just this, right? So you will get back the same answer. And I'm going to show you over here using the GC, okay? So what you can do is, okay, I'm just going to refresh the page. Okay, now here, second DISTR, go down to CDF. So automatically, this will be populated for you. This basically means negative infinity. So which is what we want, right? Because we are going from below 25 all the way until negative infinity. So yeah, the upper limit is therefore just 25. And then again, 23 is my mean value. My standard deviation is 12, right? And then I click enter. Then from here, I can minus away. Then I put in the next thing. So here, my upper limit is now 20, and then everything else is the same, right? Then I click enter here. So now I click enter one time. You see, I get back the same value of 0.5249, which is 0.525, right? So these two will give you back the same answer over here. Okay, so now that you get the idea, you can try it out double I, triple I if you want by yourself, but I'm just going to go through it right now. So if you're going to do it for yourself, please pause this video and try it. Okay, if not, I will show you how to do the rest. Lesser than or equals to 25 would just be what we did just now over here, right? You just come back here, DISTR, CDF, below than 25 will do, and then you paste, and then you enter. You get a value of 0.71814 dot, which is 0.718 to 3SF. So what this means is the whole area over here, this whole portion that I'm highlighting over here, right, has a value of 0.718. Okay, lastly, we have bigger than 21. So for triple I, probability of picking a value that is bigger than 21, note that our GC, our calculator, is not able to calculate bigger values. It's only able to calculate smaller values. So we need to do an intermediate step on our own, which is, if you think about it, let's say this green color line over here that I'm highlighting, let's say this is 21, okay? And if this is 21 and we want bigger than 21, means that effectively we want this whole region over here, right? That's what the question is asking us to find. But again, since our calculator cannot directly calculate this, what we can do is to find the complement, which is we take the value of 1, which is this whole area over here, right? The value of 1. Then we minus away everything that is not part of it to get what we want. So we can take 1 minus everything else that is not part of it. So I'm just going to write a very important feature here. Probability of x is bigger than a is the same as 1 minus probability of x is lesser than or equals to a, right? And we will usually convert into this format because this one is something that we can key into our GC. So from here, I'll just key this into my GC, right? I take 1 minus, then I will come back here. My upper limit is now 21, with the mean value still being 23, and this is still 12, right? Square root 12. I paste, I get this 0.71814 dot 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 dot. So here is 0.71814 ... which is 0.71823 and that would be the final answer to this question over here. Okay, so that's it for this. If you got any other questions, feel free to reach out through WhatsApp. If not, I will see you in the next few videos over here to try out these questions for yourself to see whether you're able to do it. I'll see you there.